Let's look now at drawing the Bode diagrams. To do this for any general function, we'll first look at two simple functions and then compose the more general case out of those two specific functions. So the first of the specific functions is the first order lag. And so for the first order lag, we have the form that looks like this. Well, it's typically written as 1 over tau s plus 1. And of course, to draw the Bode diagram, we eventually want L as the log modulus, which is calculated as 20 times log 10 of the magnitude of the function g of I omega. So if we apply g of I omega for this function, then we'll get 1 over tau I omega. So 1 over tau I omega plus the 1. And we don't like the imaginary number in the denominator, so we multiply top and bottom by the complex conjugate. So we see here 1 minus tau I omega, 1 minus tau I omega, and that gives us this form. So we can see in the denominator, the I squareds become a minus 1, and then so that's a plus overall times a minus, so that gives us a minus. And so in the denominator, we eventually get 1 plus tau squared omega squared. In the numerator, we've got the 1 minus tau I omega. And to get the magnitude of this number, we take the square of the real part and the imaginary parts. And so that's what we get there. And we can see that the denominator is equal to the numerator squared. So we can divide that, leaving us with that simple form for the magnitude ratio. And of course, looking at this equation, knowing that we need to calculate the log modulus, so we take 20 times the log 10 of this. And of course, we can rewrite this term, the term in the log modulus, we can rewrite this as 1 plus tau squared omega squared raised to the power minus 1/2. And so because it's a log, we can take the minus 1/2 in front here. So it's 20 times all that. So minus 1/2 times the 20 gives us the minus 10 here, and then the remainder of what's in the brackets there. So that's our formula for the log modulus. And to plot that more simply, we can observe two asymptotes. We can query what does L look like when omega is very small. So when omega is very small, then the 1 will be much greater than this part. And so we can say this is approximately minus 10 log 10 of 1 when omega is very small. And so log 10 of 1 is a 0. So L is approximately 0 at low values of omega. For larger values of omega, this term tau squared omega squared becomes much greater than the 1. And so we can effectively ignore the plus 1 here, leaving us with minus 10 log 10 tau squared omega squared. And then instead of working with these squares, we can take the factor 2 out in front, or the exponent 2, because it's the log of something with an exponent 2. We can take the 2 in front as a factor, giving us a minus 20 times the log 10 of tau omega. And we can separate that if we want, or we could simply say, well, the point when this L, this version of L, the point where this becomes a 0 is when this becomes a 1. In other words, when omega becomes 1 over tau. So for a value of omega equals 1 over tau, we have tau times 1 over tau is a 1. And so this becomes, this whole thing becomes a 0. And so that's the point when this is a 0. Otherwise, it has this form. And here we can see a gradient. So remember, the x-axis is log 10 omega, and we can see minus 20 there. So it's going to have a gradient of minus 20. So if we go ahead and plot that out, and please excuse me while I do this in Paint. So let's plot the L graph here. And we said that for low values of omega, we have an asymptote of 0. And this one is also 0 at the point of omega is 1 over tau. So let's mark off here that there's a point where we get 1 over tau. So let's say that's there. And I'm just going to mark that as a 1 over t here. 1 over t. And as we said, the L value is going to be 0 up to that point. So it's 0 for low values of omega, and all the way till 1 over tau, it's equal to 0. And then at values greater than 1 over tau, this equation applies. Right? So this applies, and we can see here that the gradient of this line is minus 20. Remember that the x-axis has log 10 omega. So the axis here is log 10 omega. So this axis is log, and it's sub 10, and I'm just going to write it as a W here. So that's your x-axis, and your y-axis is, of course, L. So because this is in effect our x part, and we can see the x part times minus 20, that means our gradient is minus 20. So if we go ahead and continue plotting this line, then we can see, or what we'll find is it's a minus 20. So that's the L part for us done. And of course, this is an approximation. This is working with two asymptotes. In reality, there's something of a curve that happens between these 2 points. So in reality, it's something like this, right? So, but that's a good enough approximation for L versus the log 10 of our omega. Okay, so that's the magnitude part. That's how we plot that. And we also need to draw the part for the angle. And so for the angle, we know the angle is always the arctan of this should say the imaginary part over the real parts. So the imaginary part, so let's go back to g of I omega. If we look here, I guess this is where we've actually worked out the number in terms of real parts and complex parts. So here's the real part, and here's the imaginary part. And so the imaginary part divided by the real part, the denominators can cancel, and we'll be left with tau omega divided by 1. So that's what we have here, the arctan of tau omega over 1. And there's a minus sign there because, yeah, I forgot to say that minus over there. But yeah, the imaginary part has that minus sign. So it's the arctan of minus tau omega over 1. And we can think about, again, two asymptotes. So when omega is very small, right, then this number is approximately 0. So we can say the arctan of 0 we know is approximately 0. And then when omega is very large, then this is the arctan of minus infinity. And so we can say this is approximately minus 90 degrees. So you can do it that way, which I think is a little bit formal and stiff. A better way to think of it is, what do these numbers look like? So if we think of low values for omega, that means our imaginary part is very small and the real part is fixed, right? The fixed part is always at a value of 1. It's not the actual real part because we've divided the denominators, but anyway, let's compare these two as if we are comparing an imaginary part and a real part. So for very low values of omega, our imaginary part is about 0 and our real part is fixed as a 1. And if we think about drawing that, right, think about drawing a complex number like that. We are saying that the real part is about 1. Remember, this is the real axis, and this is the imaginary one. Then we are saying the real part is a 1, and the imaginary part is about a 0. So that's a point there. And we can see the angle of this point, right? Taking this as the basis angle. The angle here is 0. So we can say for low values of omega, theta is a 0. Okay, and then if we think about larger values, so as omega becomes larger and larger, then it becomes much greater than the 1. So the imaginary part becomes much greater well, negative, in the negative sense. The magnitude becomes much greater. So the imaginary part becomes much greater. And so even though we have this offset of a 1, right, the real part is always fixed at a 1. But if we take very large imaginary parts, then this angle becomes approximately equal to this one. And so this is going all the way to this large value of the imaginary part. And so as omega goes off to infinity, this 1 here from the real part matters less and less. And now the angle becomes minus 90 degrees. So if we were to graph that, let's produce another set of axes here. So we've said for low values of theta, sorry, for low values of omega. And again, we've got the log of omega as our x-axis. So there's our x-axis, and this time it's theta. What shall we use here? Okay, I'm just going to type the name, theta. And so for low values of omega, we will have a 0. So at low values of omega, your angle is 0 because your real part dominates there. And then at high values of omega, your negative imaginary part dominates, and we get something like that. So it goes to minus 90 degrees. We should label that. Minus 90 degrees here. Okay, and again, these are asymptotes, so we should really emphasize the asymptotic nature. And let's do this as something of an S curve. Okay, and let's correct that color, right? So that's how our angle looks on this Bode diagram. And let's keep going with the next instance. So we did all this for the so-called first order lag. And if you look back at the exponential and you've got the exponential die out, then that's a motivation for it being called a first order lag. For the first order lead, instead of 1 over 1 plus tau s, we have now 1 plus tau s. And so this part is in fact easier than the earlier case. So when we take g of I omega, it's 1 plus I omega tau. And the magnitude of that then is simply 1 squared plus omega squared tau squared. So that's the magnitude. And then L is 20 log 10 of that magnitude. Again, we can rewrite this stuff in the square root as 1 plus omega squared tau squared all raised to the power 1/2, which we've done here. And then we can take that 1/2 as a product because it's the property of the log. And so we can write that as 10 log 10, 1 plus tau squared omega squared. And again, we can say when omega is very small, then this term will be much smaller than the 1, leaving us with 10 times log 10 of 1. So the 1 dominates there. And log 10 of 1 is 0. So L is approximately 0 there. And then as L goes off to infinity, then, as omega goes off to infinity, then this becomes much more important than the 1. And so the asymptote becomes this one. So it's 10 log 10, right? The 10 from there, which was simplified from there. So that 10 log 10 tau squared omega squared, we can recognize this as tau omega all squared. And so take the 2 using the property of logs in front. So we get 20 log 10 tau omega. And we can split this product like this if we want, or we could just say, well, when omega is 1 over tau, then I get the log of 0 there. So I'm going to get 0 for early values of omega up to the value of 1 over tau. And this is something we saw before. So let's use a different color for this one. So we've got this asymptote. So up to 1 over tau, we've got this curve. Oops. We've got this curve. And I'm just drawing it with a bit of an offset so as not to overwrite the other one, but both these are sitting on 0. And then coming back here, yeah, as for the second asymptote, so that's what we have. And then again, our x-axis has that function. So the gradient is a plus 20 this time. So before we had a gradient of minus 20. So in effect, we have the mirror image here. So we've got a plus 20 as our gradient this time. Right, so that's how we draw L for the first order lead. Now let's look at the angle side of it. So of course, going back to our function, and that's our function in terms of I omega. G of I omega has this form, which is already separated into the real part and the imaginary part. And so the angle is the arctan of the imaginary part, which is omega tau, divided by the real part, which is 1. And we can see here that when omega is small, then this is going to be the arctan of 0, which is close to 0. And then when omega goes off to infinity, then this is arctan of infinity, which is 90 degrees. But it's a bit better to think of it instead as this is our real part again. The real part is on 1. And as we increase the imaginary part, then this point goes off here like so. So it keeps increasing like this, and eventually becomes so large that our line is approximately pointing straight up. And now the angle is more like plus 90 degrees. So we can see it starts at 0 and then it goes through plus 90 degrees. And so if we were to graph that, we would say we are starting here on approximately 0. And again, I'm just giving it a little offset so we can see both. And then at some point, we get to a plus 90 degrees. So let's say that's approximately there. And then let's put in a little thing to make it, to emphasize these are asymptotes. Right, and there, and the wrong way around. So let's do that there. Right, so that's our asymptote. And so it's quite symmetrical, right, in these two cases, and we should label here a plus 90 degrees. So plus 90 degrees. And we can see the symmetry in these two cases. And the only difference between these two cases is that the one is the inverse of the other. So here it's 1 over tau s plus 1, and here it's tau s plus 1. So that's how we graph the Bode diagram for these two cases. And the reason we've looked at these two in particular is that, in fact, most of our functions can be posed in this form. So much like we can create a Taylor series of functions, quite often we can repose our transfer functions in forms like this, where we have multiple first-order leads and multiple first-order lags all multiplied together. And if we think about our complex numbers, and if we think about the magnitude, right, magnitudes can multiply together. So we could think about multiplying each of these magnitudes together to give us the overall magnitude. And of course, the denominator ones, instead of multiplying, those will divide. And then similarly for the angle, if we think about polar coordinates, if you multiply exponential of I times the argument, then of course, when we multiply those terms together, then we add those angles as well. So in a similar way, the angles will also add together in the numerator and they will subtract off in the denominator. So if we were able to graph each of these terms, right? So imagine we were graphing just this part. Then we would say, well, that's simply a first order lead. So I know I go until 0. So I start for low values of omega. And then when I reach 1 over tau 1, Then I have the crossover. So if that's 1 over tau 1, 1, and then I get the plus 20. So then I've completely graphed this part. And similarly with the angle, we would say it's 0 until 1 over tau 1, 1, and then we are approximately on plus 90. By the way, the transition lasts longer for the angle, so be a bit careful of that. But overall, it tends to those two asymptotes. So that's what we would do for the lead case. And then we know for the lag case, right, when it's in the denominator, then the gradient is simply minus 20 and minus 90. So we know how to graph each of these pieces. And as we've just said, in terms of taking the log of the magnitude, we can just add together all those pieces. And in terms of taking the angle, we can also add and subtract. So the numerator and denominator, we can add and subtract. So let's say we had another, let's say we had a case where we had two numerators, and let's say the other case, the line for that looked like this. So we have up till this point. So let's say that's our, let's try and get a decent color in here. And so let's say we went up to this point, and then, so let's say that was in the numerator. So we would get another plus 20. And in this case, our crossover is here. So these two lines are intended to be parallel. So overall, we would say then the net result in this case would be, if we were drawing here, we would know we would be on 0 up to this point. Then at this, in this region, we have the plus 20 canceling with the minus 20. So actually, in this case, we would continue on 0 here, and then we would get the contribution from here. So in this case, we actually have following off this remaining term. So this is simulating the case where we have an equation that looks like this. So let's say our G equals, and we have the case here where it's tau 1 s plus 1, and then we have tau, then we have tau 2s plus 1, and all of this is divided by tau 1s plus 1. So in this case, these two are canceling each other out, right? The numerator and denominator are canceling each other out, and the only thing left over is that. And in fact, we could have done that symbolically. We could have canceled those two symbolically, and then we would just get the lead there. But we didn't do that. Instead, we pretended we had the case where we did actually plot the numerator and the denominator and then the other numerator, and then that's the result we got. And so similarly for the angle, we would have those two cases. We would have also for the other numerator term, we would have an asymptote that went up to about this point, and it's in the numerator. So we would get this other asymptote. And then again, the red and the blue would cancel, leaving us with overall just the purple line. Okay, so for any function, so something with a form as general as this, that would be graphed in that way.